Thank you for joining me today. My name is Nasser Ghadiri, and I'm going to talk about patient similarity. I'm an associate professor at Isfahan University of Technology and currently a research fellow at Western Sydney University. My industrial background also covers projects in software engineering, healthcare, and energy domains. The topics today include two projects. The first project is about the patient similarity using representation learning and focusing on the temporal aspect. The method is applied to downstream tasks. And the second project further improves the first one by extracting key phrases for the concepts extracted from this charge sheet using pre-trained language models. The team members were from the Isfahan University of Technology, University of Isfahan, and the Medical University of Vienna. So what is the problem of patient similarity and what applications are considerable for patient similarity? When we have two patients, say patient A and patient B, it's a key question in healthcare domain to predict how similar are patient A and patient B based on their electronic health records. This key mechanism has a diverse set of applications in healthcare domain, including precision medicine to tailor treatments and interventions to individual patients. Also for healthcare management and resource allocation by clustering patients. Every clustering algorithm requires a patient similarity, and the more enriched the similarity measurement, the better outcome of the clustering that could be used in this case to improve efficiency, to reduce costs, and enhance patient outcomes. The other application area for patient similarity is disease surveillance, identifying clusters of cases, monitoring the spread of disease, and develop target interventions if required. And another application area is patient stratification, identifying subgroups of patients for different treatment approaches or targeted intervention, as well as many other applications. So the patient similarity is a key mechanism in this domain. So what are the challenges for computing patient similarity based on electronic health records? EHR contains two parts of data, as you know. The first part is structured data. For example, ICD codes for diseases, laboratory results, for example, fasting blood sugar or other parameters, medications, and so on. Computing the patient similarity using structured data is rather simple because everything is almost clearly defined and you can compare two patients. The second type of data in electronic health records are unstructured data that include different types of notes, clinician progress notes, discharge summaries, radiology reports, and they are more challenging to compare for different patients, requires more complex processing, especially when we need to take into account the time and temporal aspect that I will describe later. The temporal aspect of electronic health record is an important aspect because the events, the order of events that happen for every patient could contribute to many tasks, including longitudinal patient care, tracking the health status over time. Also, a good modeling of temporal with facilitate clinical decision making. A comprehensive record of patient data could enable the physicians to make more informed decisions. Also supports research and quality improvements. A more precise recording and extraction of temporal data from the EHR could help researchers to better identify trends in disease prevalence and so other options. And it also supports regulatory and legal requirements. If we have a complete record of patients' health history, it would better support the regulatory and legal requirement. So it is an important aspect of electronic health record. And what is the challenge for extracting temporal data from the electronic health record? We can see that there are different levels of temporal data that might be required for different tasks. For example, long-term trends in electronic health records that convey years or decades. The application is to identify long-term trends in disease prevalence, treatment outcomes, and so on. The next level is medium-term outcomes, analyzing data at the level of months or years. It also provides insights into patient outcomes, including the effectiveness of previous treatments and progression of disease. The next detailed level is short-term changes at the resolution of days or weeks. It also has applications in providing insight into acute changes in patients' health status and the requirement treatments. The most detailed level is real-time monitoring that could be required in cases such as ICU or emergency departments. And the challenge here is the answer to the question, what if multiple levels of time or temporal data needs to be integrated to compare the patients? Because when we are going to compare patients, we don't know in advance which level will be required. We are going to extract knowledge to be used later for similar patients. So we need a technique to cover multiple levels of temporal data at the same time. There are some existing methods, many methods for the two challenges. There are many methods for extracting data, both structured and unstructured, and for temporal aspect. Selected research works are temporal tree, developed at the University of Queensland. It considers just structured data at different levels of temporal resolution. Another research work is TAPER, developed at UCLA, that considers both structured and unstructured parts with the temporal aspect, but the representations for the two types of data are isolated. And we need a unified approach to extracting temporal data. In softwares and industry applications and cloud applications and software, we have, as far as we know, we have partial support of modeling time and temporal relations in many tools such as Amazon Comprehend Medical, Spark NLP, Google Cloud, and other tools. So there is a need for an enriched model of extracting text, knowledge from text in EHR, considering different levels of detail in temporal data. For filling this gap, we have a model that integrates structured and unstructured data using a novel tree structure based on the tree structure developed at the University of Queensland. For the first time, it produces a unified representation vector for both types of unstructured and structured data and focuses on the temporal aspect. Also, fewer studies have used external knowledge sources, for example, UMLS, to process clinical notes. We use it extensively for enriched processing. Shortcoming of some previous methods were assigning the same weights to all parts of clinical notes. In reality, we can see that different tasks and different reasoning about patient similarity will require assigning different weights to family history, illness history, or other sections of EHR. So when computing the similarity, we assign different weights based on the task at hand. And here we can see the overall pipeline that I will describe at higher level, and the details would be presented in next slide. In the first step, we get data from electronic health record, both unstructured and structured data. Then we convert it to a unified format, harmonized as entities we called quadruples that show time, the temporal event type, the event, and the value. And we differentiate three types of time aspect here. Some of the data in EHR reflect real-time data with short-term effect. Some are newly detected finding with long-lasting effect. And some are historical retrospective data. In the second phase, we have a novel key mechanism to construct the tree. Given data produced at the first step, we use a relabeling approach because we have labels in the leaf nodes of the tree. The tree is constructed according to different levels of temporal data. The higher level in tree shows the coarse resolution of time in EHR. So the higher level nodes do not have labels initially, and we use relabeling to produce labels in a bottom-up way. In the third phase, the tree is traversed to create sequences, and in the step 4, we use the sequences to generate embedding vectors to make them comparable. Currently, we use a basic technique named Doc2Vec to make the representation and compare the patients, but it could be improved in future work. And finally, at step 5, we compare any two patients based on their vectorized representation of patient similarity. Now we can delve deeper into how the new temporal tree is created. We offer two methods, UT3, that is a novel method for extracting temporal data and constructing tree from the EMR using both structured and unstructured data. It creates a tree, applies the relabeling method that will be further discussed. And the types of data that UT3 takes into account are current real-time and shown in yellow, and the effects with long-term aspects shown in red. UT3H further improves the UT3 model with historical data in EMR shown in gray. We will discuss that this historical part of data is also important in some cases. And we evaluated the proposed method for two downstream tasks, the patient similarity and the mortality prediction. Here we can see an example of the relabeling that is a key mechanism in our method. At the bottom, the lowest level of detail, we can see that we have detailed events or information extracted from the electronic health records. For example, being female and having a specific disease, having a specific level of glucose, and so on. And at upper levels, we have non-leaf nodes that are labeled using a relabeling methods based on a specific graph algorithm. The UT3 includes the data for current visit, as you can see, show in red, and UT3H further improves it by using historical data extracted from EHR for relabeling the upper levels. So when we construct this tree, as you can see, we have labels at different levels. The higher level nodes, the label names for higher level nodes are rather longer. And here we can see an example. The sequence is generated from the tree. The lowest resolution here, the lowest level of tree, the highest resolution show as sequence 1. Then sequence 2 combines combines the labels to make relabeling the second level. Sequence 3 contains even longer name labels, and at the highest level we have very long labels constructed by relabeling. All of these levels of detail and all of these labels are taken into account for computing the patient similarity. The next question to improve the method is why the history is important. Here we can see two patients. Patient 1 that we know has been pregnant, the history shows that. And the patient 2 that the disease of thalassemia had patient 2. In normal comparison, we have similar clinical manifestations when at the time of admission of these two patients, so they are considered similar. But from the history, we know that they are different and they require different treatment methods. How can we detect this difference? We need to use historical data. UT3H incorporates patient history to compare two patients for a more exact patient comparison and patient similarity. Evaluated the proposed method using a gold standard and used the final diagnosis codes as ground truths and assigned weights to the different parts of EHR and computed the similarity and compared it with ideal similarity and extracted the measures. The details could be found in our publications, but the overall results show that we have lower error, lower mean squared error using UT3 and UT3H, more precision, and a specific measure called NDCG that is improved by our proposed method. And we also evaluated the number of the effect of number of extracted words. The UT3H has better error, lower error when the number of words is increased. For the second case, we use the method for mortality prediction using 3 different machine learning methods run on the mimicry dataset. That was the basis for our work. The UT3 and UT3H performed better than existing methods, and the better classification results was produced by the XGBoost. The results can be found in our publication. As the limitations of current work and potential future work, we can say that As I said on the pipeline, we used a basic method for representation named duck-to-egg. We can use newer methods such as autoregressive GPT-like methods. It should be noted that based on a recent study for the biomedical domain, the transformer based methods performed better than GPT. So we need to consider this when using representation methods. And at a higher level, we know that because our method is based on textual data, some more complicated diseases may also require other types of data and multimodal approaches, including clinical imaging, molecular profiling, that should be added to the textual reasoning. I have also a quick overview of the second work. The problem was that clinical notes were written by people with various scientific levels and different writing styles. There are methods that help us to overcome this challenge, including name entity recognition and entity linking, but the result is a very large number of concepts. Many of them are repetitive and low value concepts. So we need a method to identify which section is more important, which concepts are more important than others for the problem at hand. And in the existing methods, most clinical concepts are as multi-word expressions. So the detection and definition of the n-gram range by the user is a challenge here. As a solution to this problem, we propose this pipeline. The discharge sheet is converted to a bag of concepts in the NLP pipeline. Then codes of concepts are processed by a TF-IDF-like algorithm to assign scores to the concepts. This will help us to differentiate more important concepts. Then we use a transformer-based representation. Here we use PubMed BERT, SciBERT, and BERT and evaluated them for the data set that we used for two downstream tasks, including multiple and binary classification by the transformer models. And compared with the key phrase extraction methods that are usually used. The proposed methods use different transfer learning methods. The SciBERT model performed better, as you can see, compared to PubMed BERT and BERT for extracting knowledge. And here we have the combination of transformer models. And as you can see, the red chart shows the SciBERT that has produced better results in combination with statistical methods. The difference could be highlighted here. Here you can see the output of existing methods. And as you can see, depending on the n-gram used, n-gram 1, 2, 3, and 4, different CUIs are created. Many of them are meaningless because they are wrongly combined the concepts, and they are different with the concepts that we require. Here you can see the result of our proposed method. As you can see, the SciBERT produced more meaningful results as we expect. You can see this paper and the source code for both papers are available. So, as a conclusion, we tackled the problem of patient similarity as a key mechanism for many tasks and applications in healthcare system. We addressed two challenges of extracting knowledge from unstructured data and focusing on the temporality at multiple levels of resolution. We addressed it by UT3, then we further improved it by UT3H that also considers historical data about the two patients that are to be compared, and it produced better results and more precise results that are essential for treatment and other purposes. Then we further improved it by key phrase methods for the concepts extracted from discharge sheets. Uh, Before this research, we had lots of concepts, and using this method, we could assign weights to extract more important concepts for a quicker reasoning about the task at hand. Thank you for listening, and you can reach me with the address mentioned here. Thank you.